Thanks. So I'm Daniel Mercier, working at AdaCore, and today I'm going to talk about how we wrote the Ada frontend for Infer. And here's the title, Type-safe Nanopasses. You will see that we wrote it by adding many small passes and in a type-safe manner, and I'm going to explain how we implemented that. So first, a bit of context, of course. Infer, we use Infer, well, we developed a front-end for Infer at AdaCore that targets seal. But first, we needed to go from source to this actual intermediate representation. And for that, we use a tool at AdaCore called libAdaLong, which is a tool that we developed at AdaCore. And that gives us a parse tree, which is a bit decorated, but it's still very close to the syntax. And you have name resolution that is already down, and you have type for expressions. So that helps quite a lot. But in this talk, I'm going to present the second part, where we went from this parse tree to the seal intermediate language. So first of all, let's start by stating how we often compilers front-ends are written. So we want to write many small or smallish passes. And for example, if you want to desugar some nodes, and you're going to iterate that until your language becomes small enough, and you can then simply translate that to your targeted language. So for example, here we're moving a while loop by simply desugaring it into a for loop, sorry, by desugaring it into a while loop with a conditional. But we want to do this in a type-safe manner, in the sense that if you have a later pass that will take as input an intermediate language that has this for loop removed, you don't want to see in the set of constructors that you have to deal with, you don't want to see that there is a for loop there. You want to see only while loops, only the kind of loops that you have to deal with. So that's what the type safety here means. So in this talk, I'm going to present you the Nanopasses framework that we actually been very inspired by a framework in Racket called Nanopasses. It's a Nanopasses framework, which is mostly used for teaching purposes. But the idea of this framework is that you write very small passes that targets removing one or two nodes or refining nodes, as I will explain. But we are doing that in a type-safe language as a camel with static typing, which is different than the framework here, which has a dynamic typing system. So to write the front end for Ada, we wanted it to be both maintainable and fully type-safe, which are both very interleaved. And so the outline of this talk, I will start by focusing on small separated passes and why do we want that. Then what do I mean by fully type-safe and why it's important for us to be fully type-safe. And then, as you might have guessed, maybe if you have a lot of intermediate languages, sometimes something that will come is boilerplate because you have to deal with the same nodes in all languages. So we want to avoid that. We want to have as small boilerplate as possible. So let's start by the small passes. So we want small passes, and I'm opposing this to a big monolithic transformation pass. And talking about that because we started by this 4 years ago when we started the Ada frontend. The first thing that we did, and it was a mistake, was to do a big transformation from what libAdaLong gives us, which is as I said earlier, it's almost a syntax tree, and there's a lot of things in Ada that you need to that are implicit in practice, and that you need to desugar. So this was hard to maintain in the end, and at the end we needed to add, for example, a feature called control types, which is similar to constructors and destructors in C++. And it was hard to add just because it was targeting from this syntactical tree to seal, and it was hard to implement. So in the end, we went the other way, the other extreme. Why not? So instead of having one big pass, we wanted to implement a compiler frontend for SEAL with a lot of passes, and in particular with passes that target small things, and each pass is doing one particular thing, one single thing, and then the compiler is simply the sequential composition or application of each of the passes that goes from one input language to one output language. So we want the passes to be correct by constructions. And as Julien told us a bit this morning, when in OCaml, when your compiler manages to compile the code, you are already happy because it catches the typing system will catch a lot of kind of bugs. Of course, this is not true in practice. You still have bugs, but it's still an interesting aspect of the language and that you want to take advantage of. And for example, here, one way of making your language more precise only by typing, in this simple example, is in the first case you have an if statement with an expression as the condition and two branches. The block here, one block is for the else part and the other is for the then part. But a better way to describe that with a better typing would be to have, instead of an expression for the condition, an actual condition, which would be a subset of the expression that are a Boolean type, basically. And as a block, an optional block for the else part, because the else part is not always here. So we want basically each pass to have its own language, because we want to take care of this, we want to have this advantage. And so one pass will take as input an intermediate language, will translate it to an output language, and the next pass will take that as an input, and so on. And each pass will have different language as input and a different language as output. So how are we going to specify all those intermediate languages? So first, how we would do that, naively, let's say, because that's not what we did in the end, you will see. But naively, or often what we are going to do in OCaml, is that we are going to use algebraic data types. Each IL fragment will simply be an expression, an inductive expression, or an inductive data type, sorry. And for example, here you have expressions within expression, the subterms are themselves expression, and so on. So you can have mutual types, you could have types that reference others, and so on. What we don't want in this fragment is that we don't want mutable states. So we want pure OCaml fragment, we'll see later why. And often people, when writing compiler frontends, they like to have what we call a back reference to the parent. So you're inside an expression, and you want to get the expression, the parent expression. That's something that we don't want, because the only way to do that in OCaml would be to add a mutable state. So instead, if you really want to do that, then you could pass the parent down the leaf of the recursive call if you really need the parent. But at least in the typing part, we don't want a mutable state, so we don't want that. So let's go to the second point, type-safe passes. Why? Why is it important? And how are we going to use that? So first, if I ask you what is this pass doing, it's pretty straightforward, only looking at its type. Because you have first a while loop, then you have a while loop and a for loop, and in the second statement you don't have the for loop anymore, so it's pretty straightforward. You are actually desugaring the for loop into a while loop, right? So one of the ways to implement the pass is simply to say that this pass is removing this node from the, it's removing this statement, so we are desugaring this statement, and you can see it through the type. Another possibility would be to refine the payload. What I call the payload is basically the types of the subterms of the constructor binob, for example, here. And in this pass, we are simply adding the typing information of sub-expression of subterms. So at the start, you had expression without information about their type, and the pass is simply refining that by adding this pair quote a tip, which is the tip of the expression. So, multiple passes also helps type safety, as I hinted a bit earlier. The fact that the language L1 and L2 are different, and when you're removing a node from a language, it doesn't appear in the next language, it's something that we can build on, because when you're writing the ends pass, you know exactly which constructor you have to deal with, and there are constructors that are impossible, and you can see that only looking at the type, it's pretty straightforward, right? So that's also very important. So in this example, the first pass will remove the for loop. The second pass doesn't have to deal with the for loop anymore. So in this example, the second pass is simply removing the condition by adding some if statements within the loop, and maybe using some gotos and labels to desugar this while with a condition. And then you go to an infinite loop. But the important information here is that each of the paths knows exactly which kind of loops it has to deal with. So now what are the benefits of this type safety? Why do we care so much about type safety? Type safety helps to catch bugs, of course. In this example, there's a bug here, and since transform is taking an expr1 and returning an expr2, the bug is pretty obvious, and the compiler will tell you that here there is a typing error because E1 is of type expr1 and it is expected to be of type expr2. This is the kind of bugs that we want to find by typing. And the other kind of bugs, and not really a bug, but more a feature of the fact that we remove the node, is that when, after you call transform on E1, you know that you have to deal only with expr2, so you don't have to deal with neg at this point because it has been completely removed. So for the last part, boilerplate free code. That's as I hinted, is very important for us because we don't want to copy paste code all over the place. And the main pitfall of having those multiple intermediate languages is the fact that you will have to rewrite your tree traversal. You will have to rewrite the recursive code and so on. If you have a pretty printer for one language, you will need to rewrite it, maybe copy paste a lot of the code to write a new pretty printer for the other language. But we don't want that. We want either to generate or reuse most of the code. How are we going to do that? So for those three cases here, the tree traversal are actually generating by metaprogramming using simple PPX. I will explain how later. And for which are mechanical, basically the tree traversal, you can look at the structure of the tree and it's pretty straightforward to look at how you are going to do the recursiveness. And we are using what is called in the functional world recursive schemas, if somebody else ever heard about it. And for the pretty printing and the partial evaluation, of course, these are code that is written by hand, and we cannot really generate those. But what we can do for them is that what we want, if you wrote, for example, earlier we saw that there was a binup in L1, and the binup was still there in L2. Then why would you rewrite the pretty printer for this fragment? You don't need to. So that's how we manage to reuse them. If at some later point you have some language as input, you could reuse most of the pretty printers that you wrote for the nodes that are in the intersection of the two languages, and just write the pretty printer for the new nodes that you added. But since we're focusing on one or two nodes, because we want each pass to remove a node or add a node or refine a node, what should we do with the other? What should we do with other nodes? In this case, that's something that we want to avoid. Here, the important piece of code here is the neg, which is being translated, but the second part is simply the recursive traverse of the tree. And that's noise, that's mechanical, and we don't want to repeat this code all over the place for each pass all going down. So this is the part that we are going to generate. But how are we going to do that? And that's where we are going to introduce a different typing manner to do that, and we introduced heterogeneous trees. Because we want to basically represent partially translated results. The pass will not take into as argument something that is not translated at all, but instead it will take something where the inner nodes have already been translated. And in this example, originally we had two loops, one nested inside the other. And the second loop, when the pass is taking the node into argument, the second loop has already been translated. So you can see in red here that the while loop doesn't have the condition anymore. So the pass that you're writing only takes into as argument something that has partially been translated, where the inner nodes represent already the result of the recursiveness. And for that, we are using recursive schemas. So maybe you spot something weird with my constructors here. We changed a bit something. We added a back quote at the start, because to do so, we need advanced OCaml typing techniques. And here we use, there are other possibilities, but that's the one we chose. We decided to use polymorphic variants. Polymorphic variants are a bit different than a regular algebraic data type, in the sense that if you have a constructor for one, in a normal algebraic data type, you have one constructor that has a name. This constructor is bound to this type. If you have this constructor in another type, they will be different because they are bound to their own types, which is not true for polymorphic variants. That's a limitation that is removed from polymorphic variants. And those types are actually only the union of their constructors. So in that case, we can use the same constructor for all the languages and without changing it, and it will be still correct and it will still type. So then what does the type looks like? So we remove completely so we need the heterogeneous tree again. So we completely removed the recursiveness of the types. We put this out of the type itself and made it parameterized. In that case, you can have a different type for the inner nodes of the expressions and the outer node. And in that case, the two expressions here, what is important is that they are, one is the subset of the other, now that we remove this recursiveness, because if we had expr2 that had expr1, expr2 inside, it wouldn't be compatible. But now it is, because expr2 is strictly a subset of expr1, so both are compatible. And we can now have a type for the inner nodes and a different type for the outer node. So what does a pass look like through its type again? So here is the type of the transform neg pass, which will desugar this neg operator. And the first line is the input parameter, the input type of transform neg. And the second line is the result of the type of the result. So as you can see, the inner node hasn't changed at all. It's still expr2, because as we saw earlier, the inner nodes are already translated, so they are already expr2. And the node that we are taking as argument is a node of type expr1, which has not been translated yet. And that's the only step that we still need to apply when writing the pass. So the pass will look like that, which is kind of cool. You only have the operator that you want to deal with. The E that the neg takes is already of type expr2, so you don't need to do the recursive call. As you can see, the transfer neg is not recursive at all. It's a simple function. And since expr2 is a subset of expr1, you can match, that's a syntactical construct. The hashtag expr2 is a syntactical construction in OCaml to match on a type. And here it matches on all constructor of expr2, which is a subset of expr1, and you can return it as it is because it's of the expected type expr2. So, any questions on this? Yeah? Because I think this is quite important.
Thanks. I wonder, is this some kind of like, you know, in C++ when you do these kind of like nanopasses, is using the visitor design pattern? Do you see any parallel between what you're doing in this design pattern?
Yeah, of course. That's something that we actually started with. There is a OCaml library called visitors, which does, it's a PPX that translates, basically it takes intermediate language and generates a visitor. But the issue with that is that for the constructors that didn't change, you still need to apply the recursive, if you want to change that constructor. If you have a binary binup in the expr1, for example, and you want the same for expr2, it won't work because you need to apply the recursive call and you need to reconstruct the new node with the subterms being recursively translated. So that's why it doesn't really work, but yeah. It's still kind of the recursive scheme that we apply. So what I didn't really say is that this is, of course, you write the pass like that, but then we have a recursive scheme that is applied to this and makes the recursive function at the end. And this is kind of a visitor. Yeah.
I had a hell of a time using Nanopass earlier this year. The whole recursive catamorphism thing really bit me, and I switched to manual recursion. So do you have an example of like the generic recursion thing? Because that's to me seems like the most complicated part. Is
what do you mean by the example?
For the subterms, like you said a generic recursor will handle them. What does that look like?
I don't have it here, but I do have the type. Yeah, I do have its type, which is a bit weird. But basically, it uses what it's using is using a map. So if you take back this slide here, and you use PPX map that would generate a map function for this, it won't generate a recursive map, right? Because it will only generate a map that would apply your function to quote A. Okay, but what you can do is do a recursive function that calls map with itself, and this is what the fold, which is called a fold, it's a generalization of list.fold basically, and this is what the recursive constructor looks like. Actually, we would like to, but we are not. We are generating the map because it already exists. But there are some caveats for generating it for a type, because here is a very simple example with one expression, but we do have mutual expressions. We have L values expressions, so they are both mutually recursive. We have different layers. We have instructions, statements, so you have all of this interleaved, and it's actually 10 lines of code that you need to copy paste each time. So it's boilerplate that is quite fine, but in the end it's still one of our goals is to make this able to generate. So just yeah.
How horrible are your type errors?
Boris made me remove this. So Boris is the colleague with whom and I had a slide with the typing error that was horrible, and he made me remove it, so I won't talk about this. But yeah, no, to be honest, the types are, so it's actually an issue, because when you're using polymorphic variants in OCaml, the typing error is kind of horrible, because it will tell you that this tag is missing. And when you're using a normal algebraic data type and you're using the wrong type, it will simply say, okay, I'm expecting expr2, you're giving me expr1. But in this case, it will tell you something like, I'm expecting binup or neg or something with things that are end with polymorphic variants in place of quote and so on. So it's kind of hard to understand, but there is something that you can do about it, is that if you annotate your types for the pass, for transform and neg, if you annotate it correctly, that's not correct typing, by the way, but but if you annotate it correctly, then the typer will tell you you will have a more correct typing error. So yeah, you need to have type annotation, otherwise it's horrible. But yeah, the Nanopasses is, you write the pass, you are getting typing errors, and then you fix them, but at the end you are pretty confident that your pass does what you want. Yeah. Yeah. So, great question. No, not the without. So so a polymorphic variant is a union of the constructors, and you can have one type which is a union of a bunch of constructors, another one that is a bunch of other constructors, and you can say that then expert3 is expert1 or expert2. That's possible. But what you cannot say is expert2 is expert1 minus neg. And that's the PPX that we wrote. So this is a PPX that we actually wrote, and is a PPX that takes like a record with del add update fields, and you tell him which one of the constructors you want to remove and add, and then it creates the type. So yeah, that's why we had to write. That's the PPX that basically we rewrote. So I have some words for conclusion, and here is a nice graph of our 36 passes, and you can see that many of them, don't look too much at the big peak, but most of them are lower than 200 lines of code, which is pretty small in the end, and they are all removing some node, desugaring some nodes, or sometimes the type doesn't really change from the input to the output, but it adds more semantic information. And the only pass that is very big is a pass that basically introduces default values for Ada objects, because in Ada, when you have a variable or an object, there is a lot of default values that you need to initialize for them. For example, pointers needs to be initialized to null. The programmer developer can specify some default values for some of his types, and so we need to include that code. And this is heavily recursive. It looks at all the typing environment, and it does and this is one of the. There's not a lot of passes that does recursive by hand, but this is one of them. And so that also means that if you still want to do recursive by hand, it's not like you cannot do it. So yeah, if there's in some cases, there are passes that are harder to write and to make them fit in this framework, but you don't have to be scared and do the manual recursive by hand. Yeah, question?
If I understand correctly, all of these passes are chained.
Yeah.
If you want to make a change after you've written all these passes, if you want to make a change in the middle, how destructive is that? How much? What's the blast radius, right? So if I wanted to change, I guess it would have to be, and I'm not just talking about a code change, actually a type change in. Yeah. Can you say a bit more?
Yeah, of course.
Yeah.
That relates a bit to the question about removing the constructor, because in the end, we also, something that we didn't really present here is that, of course, you not only want to be able to generate your traversal and so on, but you also want to express each of the passes in relation to the precedent. So, and that's what we are doing in practice. In practice, the actual union of constructors is only here for the first intermediate language, and then it's just a diff. So you add constructors, you remove constructors, you update them, and you go down the chain. So you can even reverse some of the passes, and it will still work. You can add a type at the start, and it will still work. So yeah, in the end, it really depends on the things that you are modifying, but you can go a long road by modifying a lot of things, and it will still work. But for example, if you add some constructor and you expect it to be removed at some point, you of course need to remove it because it will go down the chain. Something that we also add by the PPX is that the expert2 here, the hashtag expert2, this is pretty easy in this case, but if you remove something and add something else, the diff is not obvious. So the PPX is also adding a type that is called language_common, which are the common patterns between the two. So everything is basically derived with this PPX, and you can add a constructor at the very start of your language, and it will be fine. So yeah, to wrap up everything, I think we managed to have a type-safe nanopass in OCaml. We are pretty happy with it. And what we are happy about is also the fact that we have limited magic. We wanted to use most of the features, we wanted them to fit in the language, and we don't wanted our PPX to have too much logic in them. And because you can, if you have a bug in the PPX itself, it's hard to figure out and it's hard to fix. Well, not maybe hard to fix, but at least to figure out that the bug is there. And to give some figures, we implemented this PPX once at the start and we never touched it. So, and it's very easy. I mean, it's just, it looks at the constructors and it adds one, it removes one, and that's it. And then we are relying on the PPX map, which works well. And it's also an easy preprocessor to write. So in the end, we have very little boilerplate. The only boilerplate that we still have is those folds that we still are copy-pasting from passes to passes, but we have plans to make them also part of the PPX. And for us at AdaCore, we have this new front-end which doesn't target only seal, which is something that we wanted, but it's also interesting for us because we have now a new front-end that could be extended to target maybe other languages. And is of course easy to extend and maintain. And we added at the end, of course it was 1 year of work to re-engineer the front end, and then we managed to implement control types. Maybe we would have managed to write it at first with, with less time than 1 year, but that's it. So yeah, thank you.
So I understand you rewrote your entire front end. So you just ditched the old one and wrote a new one, or were you able to reuse some of your work?
Yeah, for example, the big pass here was actually almost not changed. So, but well, things in this pass had to be changed. But since it's only a pass that goes through the types, and we didn't change the language, the intermediate language for the types, the languages for the type is the same through all the basically the passes. The only thing that is refined is the expression statement and so on. So, but no, we still had to rewrite a lot of code, and we found many bugs in the end, also in the front end. So, yeah, bugs in the first front end that was corrected with the front end. Because the really interesting thing here is that when you're desugaring a node into a more basic one, then you can try to express semantically the things in your language with other nodes in your language. For example, in Ada we have something that's called renaming. That so you say X renames Y, and it means that whenever Y, whenever X is seen, you have to basically translate Y, and they are. So it's like X would be a pointer to Y, right? But it's not really that. But it's almost this. And yeah, you can simply write this as a pointer, and it's easier. So you remove the rename, and you have other semantics in the language that can just be leveraged to a renaming. So then you just create this renaming node, and then later passes would just handle this by themselves.
Hello. And how did you flip the switch between the two front ends? Like that seems like a pretty big operation. So you had one front end and now you have another. So were the results very different, or?
No, it was actually fine since, well, we are not executing it, thankfully, but we are still using Infer bow, but only in house, let's say, for testing the front end. So we have a big test suite for the compiler called ACATS, and we run Infer on this test suite with Infer bow, because Infer bow gives more information about values, and it was better for the purpose of testing the front end. So we had not a lot of diffs on this test suite in the end. It was actually okay so we relied on this test suite to find out if the results were good or not.
So taking a step back from the theoretical standpoint, I can certainly see a beauty of like having an algebra of those nanopasses, right? Where you could potentially not enforce the ordering of transform, but basically have a way to define it in such a way that it's actually the same result at the end. It feels like based on what those nanopasses are actually doing, it may not be possible. So I'm wondering if you ever thought about that, or if you have any interest in doing that, or whether that would simplify the implementation even further, possibly.
So is the question about the ordering of the passes?
Right. So it feels like the ordering is fixed in that case, right? Or
not really, because the answer is twofold. So first, not really, because since we are doing diffs between the input language, so we are defining the output language as a diff with the input language. So basically, we're saying the output language is this one plus this node and minus this node, or we refine some nodes. When we refine some nodes, of course, this could go down the line a lot. But if you have, for example, a pass that would desugar for loops and a pass that would desugar an egg, as in this slide, the two can be reversed with no problem. But the other answer to this question is that sometimes the order matter, because in some cases the pass will introduce more nodes, and those nodes will be translated later. And this could cause issues. For example, to give a concrete example, in Ada there's a lot of runtime checks that we want to implement to here. We want to generate code for those runtime checks. One of them being a discriminant check, which will basically check one field of a record against one value. When you access some field, you need this other field to has this value. That's what we call a discriminant check. And there is one pass here that is inserting a lot of record fields, the pass that is basically making default values for the types. But we know that the front end will generate correct field accesses. But if we put the pass that generates the discriminant check after, we are going to generate way too many discriminant checks because of the previous pass. So there are things that we cannot encode really on the typing system that enforces the ordering of the passes. But really, since we are doing those diffs in terms of typing, we could theoretically some of the passes, because of course there are some passes that would expect only this kind of loops to appear, and in that case, of course, you cannot really reverse the passes.
So maybe it's a partial order.
Yeah.
It's concept. Thank you.
Okay, I think we are done. Thank you very much.